This is video 1.2.1, and the goal of this video is to understand how to complete the square of a quadratic. So this is something you've seen before in Algebra 2, but the goal here is to kind of solidify it, make sure we're all strong in it so we're successful this year. So what is completing a square? To convert a quadratic that looks like this, y equals ax squared plus bx plus c. We're converting that quadratic into the form y equals a x minus h squared plus k. So the whole idea with the perfect square is we have this square right here, and that's where we're calling it, we're completing the square. We have to create that squared term. And remember, the h and k are very important to graphing and to understanding a key characteristic of the quadratic. So an example would be, and these equations, by the way, have to be the same. They have to be at the same value, be the exact same graph. So an example would be y equals x minus 2 squared plus 1. Well, that's the same as, it might have started out as x squared minus 4x plus 5. Those are equivalent. This is the standard form of a quadratic. This is the completed square form. And that's what we want to be able to do to convert it to completed square. We're going to be completing squares a lot this year, and it will get more complicated, but we're going to start with quadratics because that's where we're starting in Chapter 2. And we'll get into more complex squares that we'll complete as we move forward during the year. So why is it helpful? Remember, it's helpful because we can see key characteristics of graphs. And I'm not just going to talk about graphs of quadratics, but graphs of ellipses, graphs of circles, graphs of hyperbolas. So some of these you've also seen, but we want to remember that it all involves completing the square because the standard form has a perfect square in it. So let's take a look at the first example. So we're literally going to complete the square, and how you learned this in Algebra 2 was with algebra tiles. So I'm going to model the first one with algebra tiles, and then in example 2 we'll look at a more feasible way to do it for the long run here. We have x squared plus 6x minus 3. So remember, negatives are red, and positives are their respective colors, different for every type of tile. I have some extra unit tiles up here if we need them, because sometimes we need them to complete the square. So what we're literally going to do is create a square using the algebra tiles. But a couple of things to note. The tiles here, this for sure is not a square, what I've started here, because one side is longer than the other. So whatever I kind of do to the left, I need to do to the right. And this is the tedious process by which you're going to just remember and visualize what it meant to complete the square. So far I have a square. If I fill in this corner that you see down here, I would have a square. But I need to use as many tiles as I can. In fact, I have to use all the x and x squared tiles. So I'm completing the square, keeping it equal on both sides. So it looks like my square has to be of this dimension. Now, yes, I have these tiles down here, but in here, I want to see if I can fill any of those, but it looks like I can't, because one thing you should notice is that these sides are going to have to be x3 and x plus 3. So remember, it's about the length of the tile. The length from here to here is x, and then the length down here is 3. And up here is the same, x plus 3. It's a square. So in this corner over here would definitely have to be 9 unit tiles. But I can't change the value of my equation. I can't just create things that aren't there. But what I can do is create zeros. So what we do, remember, is we create zeros by pulling in a pair of positive and a negative. So I have a bunch of zeros I'm creating here. And it looks like I'm going to have to create 9 zeros in order to fill in this space down here. And my 9 zeros would end up leaving 9 reds left behind. Now remember, so I'm pulling in zeros, pairs of positives and negatives. This is the process you used when you learned how to do this. So remember, we created 9 right here, and there were 9 positives. So there are 9 negatives that were created by all the zeros. So what this means for my problem is that I've created a perfect square, and the square is going to be x plus 3 squared. But the question is, what's the constant on the outside? Well, remember these 3 negatives down here, we never touched those. It's 3 negatives plus another 9 negatives. So altogether it's minus 12. So these two are equivalent expressions. One's just written as a completed square. I didn't change the value of my original statement, but I simply added zeros. So basically I offset these positive 9 that we saw down here. We offset those positive 9 with 9 negatives. And that's one thing you have to keep in mind. We're trying to keep it balanced. So that's completed the square. I've completed the square for this first problem. X plus 3 squared minus 12. So now how are we going to do this without having tiles? Because I'm not interested in drawing 8 negative x's and 17 little unit tiles. I don't want to pull those in. I don't want to draw it. What we want to remember is, let's go back to this previous example here. What we want to remember is that we can use generic rectangles to represent this. So let's think back to our generic rectangle. We would have a generic rectangle, and we'd have the x squared. That was what was in this top left corner. And we'd have, remember, we put the 6 x's, we split them evenly because they had to make even sides. So that's going to be our first 2 steps, always for completing the square. We're going to put the x squared term in, and then we're going to split the other 2 evenly so that we have an even sides, x plus 3 on both sides. That's the whole idea, make a square. And then the question is, what did we create inside here? We created 9 in here because there has to be 9 there. But the problem originally had negative 3, so we had a negative 3 out here already, and now we have another negative 9 because we have to offset the positive 9, has to get canceled with a negative 9. So you need to make that 0, and that's really important that you create that 0 somewhere. So my problem, once again, will show up here that I have x plus 3, those are my 2 sides, x plus 3 squared minus 12. That's how we're going to do it without algebra tiles. So we're going to draw a quick generic rectangle and split up the problem accordingly. So let's take a look at example number 2. So let's try that with the generic rectangle. So we're always going to add in our x squared term into one corner. And honestly, it doesn't matter. I can do it in that bottom corner. It'll be just fine. But what's key now is to split this in half. Negative 4x in both corners. Because I need to have it equal because we're creating a square. So it's going to be x minus 4 on both sides. This is an important direction to go with this. You want to create the outsides, and then we think about, okay, what would go inside here? In this corner here, you'd have a positive 16 because negative 4 times negative 4 is positive 16. Notice that we wanted a positive 17. So in keeping with tradition, here's one way you can always do this to make sure you get it right. Always put your positive 17 on the outside, and then to offset this 16 here, we would subtract 16 because we want to cancel that positive 16. So my final completed square is x minus 4 squared. That's what the square is. And then whatever this is simplified. So in our case, positive plus 1. Eventually, you might be able to do some of this stuff in your head and kind of think about what's being created. It's this stuff in red that's the tricky part that people often make mistakes on. So we want to keep an eye on that and make sure we're not making any mistakes on that. Now for your checkpoint. So give it a shot. See if you can set up your generic rectangle and make sure you do this last step there correctly with that offsetting the positives. Remember, we watched the video if you want to see it again, or maybe do the checkpoint while you watch example number 2. because that's probably the process you'll be using in the future, not the generic, not the algebra tiles. So bring in your questions into class and make sure you have your check pointed attempted when you come to class tomorrow.